Give you a hint, this arrow is pointing to a word that says pump. Another hint that says Broad Street. You recognize Broad Street? Yeah, right. So this is London. This is the first and probably the most famous epidemiological study where a guy named John Snow, there was a cholera epidemic going on in London, and they were doing everything they could to try to combat it. And he came up with this theory that it was from contaminated well water, and that was because of improper disposal of sewage that was contaminating the groundwater. And what he did is he made a map where he made little bars here. It's a nice representation of data. He looked at all the residences and looked at where the cases of cholera were happening, and kind of made this. And he made this map to try to convince the authorities to do something. And the size of the bars here, this household got really whacked with a lot of cases of cholera, and so that they all focused around that pump. In those days they didn't have a water distribution system, so people were walking to the nearest well. So this line then drawn is sort of the line of equal distance to the next well, right? So all these people that lived within that boundary, this was the closest well for them to walk to. Right, and he showed that it was really concentrated on that well, and the story goes that he couldn't convince the authorities, so he went out and just took the handle off the pump, and then the cases started getting better. The cholera epidemic started getting relieved. So, and it wasn't until sometime later in the 1870s that Robert Koch demonstrated that disease was actually caused by microorganisms. So John Snow didn't understand what was in there that was causing the problem, but he thought there was something in there. So we are mainly concerned with removal of microorganisms from drinking water. Historically, that's been the biggest deal. It's made the biggest improvement in public health protection. I don't need to go into a whole range of the different bacteria that can cause disease, but not only bacteria, but higher organisms like Giardia and Cryptosporidium. We'll talk about it a little bit more in a second. More recently, we're more concerned with things like lead, arsenic, Flint, Michigan being a notable example recently of lead. Arsenic, Albuquerque has high arsenic concentrations in its groundwater. And then also organic chemicals. Sometimes we get contaminated groundwater. Sometimes we have trace contaminants, which we'll talk about, and by that I'm talking about pharmaceuticals and these kinds of things. So this would be familiar to you if you took the drinking water plant. So this is, I'm not going to talk a lot about treatment, but just to show you, this is, we've got all these things we need to get out. We're pulling water out of the Rio Grande, this very turbid, mucky water. We need to turn that into something that you'll drink out of your tap, right? And we're combining that, we're blending that with groundwater, which has things like arsenic in it. So how do we get those things out? And it's just a series of unit processes, large settling basins to get out all of that suspended material that the Rio Grande is visibly contaminated with, flocculation, ozonation, and then filtration, and then add a little bit more chlorine and send it out to your tap. And this would be what you saw on the tour. So these big settling ponds really take up most of the real estate out there. And if you, I should have put in an aerial of the wastewater plant. It's much more complicated. It's such a nice, compact little footprint in the wastewater plant. If you were to draw it and then draw all the flows, it'd be arrows going around every which way. But similar idea, though. You have a series of unit processes.
Are the sludge drying beds from the clean out of the settling pond?
They are, I asked if they ever have to go in and dredge those out, and I guess not in the foreseeable future. Like what that is from this flocculation here. So they're adding, they settle out all the big stuff here, but it's still kind of turbid when it comes out, and they have this cool active flow system, but they add a little chemical that precipitates out stuff that's still suspended, and you can see how red that is there. That's partially from they use an iron to precipitate stuff out, right? Okay, so how do we regulate contaminants? So this would be, the name's Phillips definition of quality at the beginning. where we're trying to conform to a standard. So the EPA sets these national regulations that any distributions, any water provider has to conform to if they're above a certain level. And so the main regulation of interest is these maximum contaminant levels. And so these are enforceable regulations, and they're based both on health effects and the cost to achieve a benefit. There's several other ones that are or a couple other ones here that are non-enforceable. One that they note is just the maximum contaminant level goal. So it's the same thing as the MCL, but now it's a goal. It's non-enforceable. It's kind of for information purposes. It's like if we had all the money in the world, what would the number be at, right? So this is health-based, not based on cost. And then finally, there's secondary standards, which are based on aesthetics. So the guidelines for water utility to, since Megan's started in charge of QA/QC, you can correct me when I'm wrong on any of this stuff afterwards, quietly in the corner. Okay. So this is based largely, we can see, on aesthetics or other non-health aspects of the water, such as the tendency to be corrosive, or an odor, or pH, or that kind of thing.
So what would be a non-enforceable contaminant?
So it's not the contaminant that's well, the secondary standards do have non-enforceable contaminants. Yeah, I was going to say it's not the contaminant. Up here, it's not the contaminant itself. For example, we'll see arsenic would have an MCL and an MCLG. Every contaminant would have both of these listed, which I'll show you in just a second. But then the secondary standards, like I say, they'll have something like odor. Odor does not show up here, but it might be a limit on like an H2S concentration. And that's partially because, you know, the public would, before you got to a health effect, the public would really rebel. So it's kind of a non-issue. So this is from the latest available drinking water report. Did you put this together, Megan?
No, we just finished our 2016.
Oh, okay, gotcha. I looked for it on the website. I didn't see it.
Well, we didn't just, it's like in print tomorrow.
Oh, cool. Wow.
Let me get it in your mail.
Exciting. Can't wait to check the numbers.
Public service announcement.
So it is. They put out a really good report. I use it in my teaching. It actually explains things very clearly. But so this is an example of this. So here we see some things that are regulated, and they don't list everything that is regulated, but kind of the main things that are concerned for Albuquerque. So total coliform, that's a measure of our bacteria that's in our sample, and this is something that's detected at, they say, distribution systems. These are samples that are taken at the tap, right? So to account for if there was any, you know, regrowth in the system or something like that, you need to regulate it at the tap. So here's how they did. Well, here's the MCL, maximum contaminant level. Presence of coliform bacteria in 5% or more samples in any month. So you can't do more than that. It sounds really lenient, doesn't it? It's like 5% of the samples can have some bacteria in them. But just though it's a conservative measurement for pathogens. So it's what we call an indicator measurement, indicator species. So that's been deemed to be safe. And Albuquerque's doing much better. They're down to 0.41%. And then here's the example of the maximum contaminant level goal would be 0. You'd like to be at 0. But you can never measure 0, right? So you always have to, you know, often the MCL is 0. For example, anything that's a carcinogen, the MCLG is 0. But you know, you can't set the standard to be 0 because that's just the limit of detection there. Okay. So how are these set then? So the Safe Drinking Water Act is the federal law that empowers the EPA to set these maximum contaminant levels and gives them the authority to set them for water utilities. So they base this on doing a health risk assessment. So this health risk assessment, or HRA, is based on all the knowledge they can get on toxicology, epidemiological studies, often on human experience, calculating exposures quite often, and they're targeting usually the most vulnerable population. So it's often children or pregnant women or people with compromised immune systems. In addition to that, you would do a health risk reduction cost and analysis. So this would be considering the health risk assessment, and now you consider, what